Hello everyone, I'm Karim Akasha. I'm a student from the German University in Cairo, and I am here in Schmalkalden during my exchange semester doing my bachelor project. I would like to welcome you all to my bachelor presentation titled Design and Implementation of Self-Optimizing Filament Setting Determination for a Sustainable FDM Process. The presentation will go as follows. I will begin by giving a brief introduction, stating the problem we have within hand and what was the goals of this thesis. And then I would give some basic background information which be needed in order to understand the work that was done during the time frame of this thesis, which would be discussed in the third part of this presentation. And then I would finish off with the results and conclusion. With the increasing number of world population, our consumption increases with it. As it can be seen from this graph, in the year 1970, our consumption have matched Earth's natural resources, and as can be seen from the trend of the curve, the gap is only getting larger. According to the Organization of Economic Cooperation and Development, our usage of raw material would be doubled by the year 2060. One of the approaches that can be taken to combat such threat is the 3R approach, which is to reuse by finding another usage for the products after their end of life, even if it would be of another functionality. Second one is to reduce by reducing our production of waste by trying to achieve our objectives as minimal as possible. And the last one is to recycle by reintroducing the products after their end of life back into the manufacturing process. One of the industries which produces in huge volumes is the plastic industry. As it can be seen here, by the year 2015, our production of plastic has exceeded 350 million tons per year. One of the forms of the plastic industry is the FDM additive manufacturing process. And one of the obstacles which faces us when trying to recycle the plastic resulted from this process is that the recycled plastic properties differs from the pure plastic. So, when trying to use the printing parameters of the pure filament on the recycled one, we obtain bad quality. So the goals of this thesis is to propose a recycling cycle to be low cost and can be done on site in order to be suitable for small and medium enterprises, and also to design and implement a process in order to be integrated with the FDM additive manufacturing process to be able to determine the new printing parameters. The dangers of the plastic waste is not only in its volume, but also its effects on our environment. For the plastic footprint, the term footprints mean the metrics which is used in order to capture the effects of an activity, as well as indirect effects that propagate through the supply chain. As it can be seen here, represented in the black curve, the total amount of plastic waste generated, and in the blue curve, the only amount of the plastic waste which was recycled. As you can see, there is a huge gap between them. Our process takes place in the environment of Industry 4.0, and from its name, it is not the only one. The industrial revolutions began with Industry 1 by the introduction of machinery and steam power, Industry 2 by mass production, Industry 3 for the introduction of automation, Industry 4 it introduced the cyber physical systems, and finally Industry 5 which introduced the human element in the cyber physical systems. By taking a closer look into the Industry 4.0, we can see that it depends on a lot of pillars. However, we are interested in only two of them. The first one is the Industrial Internet of Things, which would enable the machines to be able to communicate with each other, and this would be utilized in the recycling cycle. And the second one is the additive manufacturing. Additive manufacturing can be compared to its counterpart, subtractive manufacturing, or what we can call normal manufacturing method. Where in subtractive manufacturing, we will begin with a block of material, start removing materials from it until we reach our final product, and then a lot of waste would be generated. However, in additive manufacturing, we begin with a certain amount of materials and then build up our product until we reach our final form of the product and little waste is generated. One of the forms of additive manufacturing is the FDM process, as mentioned earlier. And to simply understand the FDM process, it takes a plastic filament, melts this plastic, and then build the product layer by layer. In the environment of Industry 4.0, we can apply what's called self-optimization. A self-optimizing system means a system which can adapt to its changing environment and set new goals for itself. This can be done through either by adjusting its own parameters or by changing its internal structure. Self-optimization has three steps. The first one is the analysis of current situation, where it monitors how the variables are changing. The second one is the determination of objectives by setting new goals for itself. And the last one is the behavior adaptation, where it sends out orders and signals to the various parts of the system with the new required behavior. One of the techniques which is used in this thesis is what's called thermal imaging. Thermal imaging is a non-contact temperature measurement method where it is used to measure the temperature of a target within a distance. As it can be seen to our left-hand side is a normal optical image where visible light is used to capture it, and to our right-hand side is the thermal image where infrared radiations is used to capture it. And then the values of the temperature is translated into color in order to be able to visualize it. Thermal imaging has two types. The first type is the active thermography, where an outside heat source is needed in order to heat up our target to be able to further study it. The other type is passive thermography, where the target exhibits its own heat and there is no need for an outside heat source. Moving on to the work that was done during the thesis, first we would present the proposed recycling cycle. Our recycling cycle consists of 5 main steps. The first one is the scrap collection, where plastic waste and scrap is collected from its various sources, and then moves to material grinding, where the raw material that's needed in order to manufacture a filament should be the size of a small pellets as seen in this picture, and we can bring the plastic parts down into these small plastic pellets by using what's called a grinding machine, as can be seen in the photo to our right. After material grinding comes a stage of material mixing, where for some products it requires a certain level of quality which cannot achieve using recycled plastics only. So a certain amount of pure plastic should be mixed with it in order to be able to achieve the required quality levels. The fourth step is the filament extrusion, uh, where the small plastic pellets is introduced into such a machine, which melts these pellets and then extrude it into the form of filament. And this machine and the one shown above are both available here in Hochschule Schmalkalden. After filament extrusion comes the last step of the cycle, which is filament loading. By reintroducing our recycled filament back into the printing process by loading them into the printers. And to close the cycle, we take the plastic waste and scrap generated from our printing process back into the scrap collection phase, along with external plastic, as long as they are both of the same material. As mentioned before, when using incorrect printing parameters, some defects might occur. This thesis focuses on three types of these defects. The first one is overheating, when the plastic is melted at a higher temperature than the one which is supposed to. The fluidity of the plastic increases, which would lead for the filament to occupy more space on the printed board. The second defect is under extrusion, where the printer lays little filament on the printed board. And the last one is clogged nozzle, where the nozzle itself is clogged and there is no filament inlaid at all. What's common between the three defects that they all can be detected through the filament width. In order to be able to detect these defects, three approaches can be taken. The first one is thermal imaging, and as mentioned before, this is the approach that was applied in this thesis. Other possible approaches was computer vision and image processing. However, in this approach, a separate training set would be needed for each type of defect, which would add more and more processing power, which would be required in order to conduct this approach. And also the variation in the lightning conditions may affect the results. And the third approach was by utilizing the pressure and temperature sensors, where we can insert the readings of the pressure and temperature of the molten plastic into some set of equation in order to be able to calculate the viscosity of the molten plastic. And from the viscosity, we can detect which defect has occurred. However, as mentioned before, when the plastic is recycled and it passes on some processes, its properties changes. So these equations may not be reliable. And for the previously stated reasons, thermal imaging was chosen to be applied in this thesis. The detection of these effects by using thermal imaging would go as follows. At first, we would begin by experimenting with a pure filament in order to be able to determine where the filament exists in our thermal image and how many pixel columns does it occupy in the filament width. And after that, in order to be able to detect overheating, we would find that the filament heat signature occupies more pixel columns than expected. For under extrusion, the filament heat signature would occupy less pixel columns than expected. And finally, for the clogged nozzle, we wouldn't be able to detect any heat signature at all. Presented here is the normal workflow of the printing process, where it begins with the machine interface in order to get the input from the user and information about the print. And then this information would be passed through our control system, which would control the printing parameters. Three printing parameters was chosen to be controlled in this thesis, which is the temperature, printing speed, and filament feed rate. In order to be able to deal with the overheating, temperature should be reduced, and to deal with under extrusion, both temperature and filament feed rate should be increased, and printing speed should be reduced. And finally, to deal with the clogged nozzle, temperature should be raised. And after the control system set the parameters, the printing process occurs, and then we obtain our product. By taking a closer look into the control systems, we can see that it depends on simple control loops, where the reference signal is always constant. However, what's changing is the error. And the error is the difference between the reference signal and the output signal. But again, this control loop cannot change its own reference signal. Presented here is the process workflow after the introduction of self-optimization. The self-optimization process would begin by detecting the optimization potential in the filament quality monitoring phase, and then pass this optimization potential to our self-optimizing control in order to analyze these potentials and try to adapt the system to its new situation based on the detected defect and see which parameters should be changed and by how much. And then it would send out the new reference signals to the control system. I would like to recall this slide from earlier in this presentation. By applying self-optimization in our project, it will look as follows. For the analysis of current situation, it would be what defect was detected. And for determination of objectives, it would be which parameters need to be adjusted and by how much. And finally, for the behavior adaptation, would be sending out the new reference signal to the control system. In order to be able to determine the new parameters, two algorithms was designed. The first one is a rule-based algorithm where the parameters is changed by arbitrary values based on some conditions related to which defect was detected. The other algorithm that was designed is depending on interpolation process, where we give numerical values for the filament width. For example, if the filament width occupies 2 more pixel columns, it would be given a numerical value. If the filament width occupies 1 less pixel column, it would be given a different numerical value. And through that, we can obtain set points. Taking temperature, for example, in our algorithm, we would take 3 set points, one at a high temperature, one at a low temperature, and one at optimal temperature. And through these three set points, interpolation can take place, an equation can be formed, and this equation would be updated each time we obtain a new set point. And by depending on interpolation, we can reach the new printing parameters in a faster manner than the rule-based algorithm. And by giving numerical values for the filament widths, we can apply what's called KPIs or key performance indicators. Key performance indicators is a technique used in order to compare how well our system is performing compared to our expectations. And after giving a numerical value for the filament width, it can be taken as one of the indicators, along with other indicators that can be decided in the future. We can have a better control over the filament quality and of the overall product. For the sensors and the processing units used in this thesis, for thermal imaging, Melex's 9640 thermal camera was used with the 32 by 24 pixels. It is operated through Arduino Zero, as this camera requires at least 20 kilobyte of RAM in order to operate. And Arduino Zero provides 32 kilobytes of RAM, which would be enough in order to operate the camera efficiently. Other alternatives that was available for the camera was the Flare Lepton 2.5 with 80 by 60 pixels. It would give a better resolution, however, it was 5 times more expensive. The other alternative was the ANG 833, however, it had low resolution and it couldn't be used in the project. Presented here are some results that were acquired. Open testing for overheating. We have to our left a printed filament at the optimal setting, and to our right a printed filament at the temperature of 240 degrees Celsius. It can be seen in the picture to our left. At optimal settings, the filament width averages between 5 to 6 pixels. However, at temperature of 240 degrees Celsius, the filament width averages between 7 to 8 pixels. Presented here is two test prints. The one on the left is at optimal settings, and the one to the right is at 240 degrees Celsius. We can see that there is a difference in the quality between both of them. By taking a closer look into the test print to our right, which was printed at 240 degrees Celsius, we can see that the filaments are fused together. And here are test prints when trying to test for under extrusion by using lower temperatures. However, the prints failed due to the low temperature used. And in our case, we need to use higher temperature differences in order to induce higher variation in the filament width in order to be able to capture it with our low resolution camera. So to sum up, recycling plastic is a vital process to combat the increasing amount of plastic waste. A low-cost recycling cycle is proposed for small and medium enterprises. A self-optimizing parameter determination was designed, and we were able to detect a difference in the filament widths open testing for overheating. In addition, for the work that was done during the time frame of this project, future work may include finding a way to update the printing parameters online while the printer is running, and also using a high resolution camera in order to be able to detect lower variation in filament widths, to be able to use lower differences in the parameters to be closer to the real life situation. So that's it for our presentation, and I would like to thank you all.